Welcome! In today's session, we'll explore an interesting problem called last person to fit in the elevator. This problem challenges us to analyze weights and determine the maximum number of people who can safely fit in an elevator without exceeding its weight limit. Let's dive into the details. In this problem, we are tasked with determining the index of the last person who can fit into an elevator without exceeding its maximum weight capacity. You are given an array called weights, where each element represents the weight of a person in the order they arrive. Additionally, you have a value called max weight, which specifies the maximum weight the elevator can hold. The elevator starts empty, and people are added one by one based on their order in the array. If adding someone causes the total weight to exceed the maximum limit, the process stops immediately. The goal is to find the index of the last person who was successfully added to the elevator, or return -1 if no one can enter at all. The problem is constrained so that the length of the weights array and the values of weights and max weight are all within reasonable limits for computational efficiency. Let's consider the first example to understand how the solution works. The input array is weights equals 40, 50, 150, 80, and the maximum weight capacity of the elevator is 200. Initially, the elevator is empty. The first person, weighing 40, enters, bringing the total weight to 40. Then, the second person, who weighs 50, steps in, increasing the total weight to 90. Next, the third person, weighing 150, attempts to enter. However, their addition would push the total weight to 240, which exceeds the limit of 200. As a result, the process stops at this point. The last person who successfully entered the elevator is the second person, at index 2. Thus, the output is 2. Now, in the second example, the input array is weights equals 100, 100, 100, 100, and the elevator's maximum capacity is 300. Initially, the elevator is empty. The first person, weighing 100, enters, bringing the total weight to 100. Then, the second person, also weighing 100, enters, making the total weight 200. The third person, with a weight of 100, enters next, bringing the total weight to exactly 300, which matches the capacity. At this point, the elevator is full, and the fourth person, who also weighs 100, cannot enter because their addition would exceed the limit. Therefore, the last person who successfully entered is the third person, at index 2, and the output is 2. In the third example, we are given weights equals 300, 400, 500, and a maximum weight capacity of 200. Here, the very first person, weighing 300, cannot enter the elevator because their weight alone exceeds the maximum capacity. Since no one can enter, the elevator remains empty throughout the process. In this scenario, the output is -1, indicating that no one was able to fit into the elevator. There are a few important edge cases to consider in this problem. First, if all the weights in the array are larger than max weight, the output should be -1 because no one can enter. Similarly, if the very first person's weight exceeds max weight, the output is also -1 since the process stops immediately. On the other hand, if the total weight of all people in the weights array is less than or equal to max weight, then everyone can enter, and the output would be the last index of the array. Finally, if there is only one person in the array, the output will depend on whether their weight exceeds max weight or not. These cases ensure that we handle every possible input scenario effectively. When tackling this problem, the brute force approach is a straightforward method to consider. The intuition behind it is simple: we simulate the elevator's operation by sequentially adding each person's weight, keeping a running total. If adding another person causes the total weight to exceed the elevator's maximum capacity, we know the last person who fit was the one added just before. To implement this, we initialize variables to track the current total weight and the index of the last valid person. Then, as we iterate through the weights array, we add each weight to the total. If the total exceeds the capacity, the process stops, and we return the index of the last valid person. Otherwise, we continue updating the index until all weights are processed. This method is efficient in terms of time, with a complexity of O(n), as we only pass through the list once, and it uses constant space since no additional data structures are required. While simple, this approach directly mirrors the problem's sequential nature and provides an intuitive solution. Now, while the brute force approach is efficient, there are cases, especially with very large inputs, where we might want to explore optimization. One such strategy involves using a cumulative sum array. By pre-computing the running total of weights, we can quickly determine the point where the total exceeds the maximum capacity. This involves creating an array where each element represents the sum of all weights up to that point. Once this array is built, we can iterate through it to find the last index where the sum remains within the allowed capacity. Alternatively, if the weights are sorted, we can further optimize by applying binary search on the cumulative sum array. This allows us to efficiently locate the largest index where the total weight does not exceed the elevator's limit. However, this binary search requires the weights to be sorted beforehand, which adds an extra pre-processing step and a time complexity of n log n for sorting. While helpful in specific scenarios, this approach introduces additional space and pre-processing requirements, which may not always be ideal. Given these considerations, the brute force approach stands out as the chosen strategy for this problem. It is directly aligned with the sequential nature of the task, where weights are evaluated one by one, just as people would enter an elevator in real life. This method is straightforward to implement, avoids unnecessary pre-processing, and ensures space efficiency by not requiring any additional arrays. While alternatives like cumulative sums and binary search offer theoretical advantages in specific situations, they do not provide a significant improvement in time complexity for this problem. Furthermore, these approaches introduce added complexity, which is unnecessary given the simplicity of the problem constraints. By choosing the brute force approach, we strike a balance between clarity, simplicity, and optimal performance for the given requirements. Finally, the key insight that simplifies this problem is understanding that it revolves around maintaining a running total of weights and identifying the last person who fits within the elevator's capacity. This realization eliminates the need for more complex solutions, as the answer naturally emerges during a single traversal of the weights array. By keeping track of the cumulative weight and stopping as soon as the limit is exceeded, we solve the problem efficiently and intuitively. In conclusion, the brute force approach is optimal for this scenario, offering both time and space efficiency. Alternative strategies, while interesting, add unnecessary complexity without delivering significant benefits. This solution emphasizes clarity and simplicity while achieving the desired performance, making it an excellent choice for this problem. To approach this problem, we need to determine how many people can enter the elevator before exceeding its maximum weight capacity. Imagine we have an array of weights representing the people waiting for the elevator. Alongside that, we have a maximum weight limit, max weight, which the elevator cannot exceed. The task is to sequentially add people to the elevator, one at a time, until adding another person would cause the total weight to surpass this limit. At that point, we stop and return the total number of people who successfully fit. To implement this, we start by initializing two variables, current weight, which will keep track of the cumulative weight inside the elevator, and count, which will count the number of people added. Both of these are initially set to 0. This setup ensures that we have a clean slate to begin evaluating the weights step by step. Now, to process the weights, we iterate through the array one person at a time. For each weight, we check if adding it to the current total weight, current weight, stays within the maximum allowable weight, max weight. If it does, we update current weight by adding the new weight and increment the count to reflect that another person has been added. However, if the new weight would push the total over the limit, we stop the process immediately by breaking out of the loop. This ensures that we don't waste time processing further weights when it's already clear that no more people can fit. Once the loop ends, either because we've finished checking all the weights or because we broke out early, we return the count variable, which contains the number of people who successfully fit within the elevator's capacity. This algorithm is efficient and straightforward due to a few key insights. First, it operates under the assumption that the weights are considered in the order they appear in the array, meaning there's no need to sort them. This helps keep the algorithm simple. Second, the ability to terminate the loop as soon as the maximum weight is exceeded adds to its efficiency, as we avoid unnecessary calculations. From a performance standpoint, the algorithm processes each weight exactly once, making its time complexity n, where n is the number of elements in the array. Additionally, its space complexity is 1, as it operates using only two scalar variables, current weight and count, without requiring any additional data structures. The data structures used in this problem are minimal. The input array weights is the sole data structure, containing the weights of all the individuals. Beyond that, we rely on two simple variables: current weight, which keeps track of the total weight of people already in the elevator, and count, which records the number of people added. Both of these are scalar values, meaning they occupy constant space. This simplicity in data structures is one of the reasons why the algorithm is both efficient and easy to implement. When solving this problem, it's important to consider a few edge cases. First, if the weights array is empty, there are no people to add, so the algorithm should immediately return 0. Second, if every weight in the array is greater than the elevator's capacity, no one can enter, and the algorithm will terminate after the first check, returning 0. Another scenario to consider is when the cumulative weight exactly matches the maximum capacity. In this case, the algorithm will allow the last person to enter before stopping. Finally, for an array with only one person, the algorithm simply checks whether their weight fits within the capacity, which ensures correctness even for the smallest possible input. These considerations ensure the algorithm handles all possible inputs robustly and reliably. This Python implementation solves the problem of determining the number of people who can fit in the elevator without exceeding the weight limit. The last person to fit method iterates through the list of weights, tracking the cumulative weight in the total_weight variable. It also maintains a count of how many people have been added to the elevator. For each weight in the input list, the method checks if adding the weight to the current total would exceed the maximum allowable weight, max weight. If it does not exceed, the weight is added to total_weight, and the count is increment. If it exceeds, the loop breaks, and the method returns the count. This approach ensures the solution is efficient, running in O(n) time complexity, where n is the length of the weights list. Edge cases, such as an empty list or very small maximum weight, are naturally handled by the loop condition and the initialization of the total_weight and count variables. This is the Java implementation of the last person to fit in the elevator problem. The logic mirrors the Python implementation, with the key difference being Java's requirement for explicit type declarations and the use of Javas for each loop. The method iterates through the array of weights, keeping track of the total weight and counting how many people can fit within the maximum weight limit. If adding another person exceeds the limit, the loop breaks, and the method returns the count of people who can fit. Here, we begin with a basic example to understand the problem. The input consists of weights 50, 60, 70, 80, and a maximum weight limit of 150. We initialize two variables, total_weight to keep track of the cumulative weight, starting at 0, and count to record the number of people who can fit, also starting at 0. Now, as we iterate through the list of weights, the first person with a weight of 50 is considered. Adding this to total_weight results in 50, which is less than or equal to the maximum weight, so we update total_weight to 50 and increment count to 1. Next, we check the second person, whose weight is 60. Adding this to total_weight gives 110, which is still within the limit. Thus, we update total_weight to 110 and increment count to 2. When we consider the third person with a weight of 70, adding this to total_weight results in 180, which exceeds the maximum weight of 150. At this point, we stop the iteration, as no more people can fit in the elevator without exceeding the limit. The final result for this example is straightforward. The count variable, which tracks the number of people who successfully fit in the elevator, is 2. This means the last person to fit is the second individual in the list. Therefore, the function returns 2 as the output. Now, let's move to a second example where the input weights are 30, 40, 50, and the maximum weight allowable is 200. Once again, we start by initializing total_weight to 0 and count to 0, preparing to iterate through the weights. In this case, the first person has a weight of 30. Adding this to total_weight gives 30, which is within the max weight of 200. We update total_weight to 30 and increment count to 1. The second person has a weight of 40, and adding this results in 70, which is still within the limit. We update total_weight to 70 and increment count to 2. The third person weighs 50, and adding this to total_weight gives 120, which remains under the max weight. We update total_weight to 120 and increment count to 3. Since we've processed all weights and none of them exceeded the limit, the final result for this example is 3. This means all 3 individuals fit in the elevator, and the function returns 3 as the output. Now, consider the third example where the weights are 100, 200, 300, and the maximum allowable weight is just 50. We start by initializing total_weight to 0 and count to 0. As we begin iterating, the first person has a weight of 100. Adding this to total_weight results in 100, which exceeds the max weight of 50. Since the very first weight is already too heavy, we stop the iteration immediately. In this case, no one fits in the elevator, so the final count remains 0, and the function returns 0 as the output. To summarize these examples visually, in the first case, the iteration stops when the cumulative weight exceeds the maximum. By the second iteration, total_weight reaches 110 and count is 2. Adding the next weight would exceed the limit, so we stop. In the second example, all weights fit within the max weight, resulting in a count of 3. The third example demonstrates that if the first weight already exceeds the limit, no one fits. The key takeaway here is that the loop ensures we only add weights that stay within the limit, breaking immediately once adding the next weight would exceed it. The count variable effectively tracks how many individuals fit in the elevator, and this value is returned as the final result. To analyze the time complexity of this solution, let's start by considering the input size. If we denote the number of elements in the weights array as n, the algorithm processes each of these elements exactly once. During each iteration of the loop, only constant time operations are performed, such as updating the cumulative weight, comparing values, and incrementing a counter. In the best-case scenario, where all the weights fit within the maximum allowable weight, the loop completes n iterations, resulting in a time complexity of O(n). Even in the worst case, where the cumulative weight exceeds the limit at some point, the algorithm still iterates through all n elements before reaching a conclusion. Therefore, the overall time complexity remains O(n), as the number of operations is directly proportional to the size of the input array. Now, let's shift our focus to the space complexity. The algorithm uses 2 auxiliary variables, total_weight to track the cumulative weight and count to keep track of the number of people who can fit. Both of these are simple integers and require a constant amount of memory, or O(1), space. Additionally, the algorithm operates directly on the input weights array without creating any new data structures, meaning no extra memory is allocated for storage. As a result, the overall space complexity is O(1). To put this into perspective, a naive approach that tests all possible subsets of the weights array could have a time complexity of O(2 to the power of n, due to the exponential growth of subsets. In contrast, our solution avoids this by iterating through the array linearly and maintaining a running sum, making it far more efficient both in terms of time and space. Let's break down the best, average, and worst-case scenarios for this algorithm. In the best case, all the weights fit within the max weight limit without exceeding it at any point. Here, the loop completes exactly n iterations, resulting in a time complexity of O(n). In the worst case, the cumulative weight exceeds the limit after processing some elements, causing the algorithm to stop early. However, even in this scenario, the loop still iterates up to all n elements, so the time complexity remains O(n). On average, the algorithm will process a portion of the array before reaching the weight limit, but since this is also proportional to n, the complexity does not change. Mathematically, the for loop contributes O(n) iterations, and each iteration involves constant time operations, resulting in an overall complexity of O(n*(O1) equals O(n). Additionally, because no extra data structures are used and auxiliary space is constant, the space complexity is confirmed as O(1). When solving problems like this, there are a few common mistakes to watch out for. First, overlooking edge cases can easily trip you up. For example, what happens if the input array is empty, or there's a single weight, or a weight exceeds the elevator's capacity? These scenarios might seem rare, but they often expose gaps in your logic. Ignoring them could lead to runtime errors or incorrect results. Next, failing to optimize for large inputs is another frequent error. If you rely on a brute force approach with high time complexity, like O(n²), it might work for small inputs but will likely time out when you're dealing with larger datasets, especially when n is very large. Another issue is incorrect summation logic. If you don't reset the running total at the right time or misplace the logic, you might exceed the weight limit or stop processing prematurely. Finally, off-by-one errors, such as using the wrong comparison operator or starting a loop at the wrong index, can lead to subtle bugs that are tough to debug, particularly in scenarios involving cumulative sums. Now, let's focus on a few more variations and tips. When the problem allows it, not considering sorting the weights can make things harder than necessary. Sorting, for instance from lightest to heaviest, can simplify the logic significantly and enable more efficient strategies like a two-pointer approach. Recognizing patterns in the problem is also key. Many elevator or weight distribution problems boil down to optimizing a sum under constraints, so look for patterns involving subsets, cumulative sums, or greedy strategies. During interviews, it's also important to ask clarifying questions. For example, can the weights be reordered, or does the elevator have constraints like a maximum number of people? These details can significantly affect your approach. Efficiency is critical, so always analyze the time and space complexity of your solution. An n-log-n method, such as one that uses sorting, is often a good balance of efficiency and simplicity compared to something like n-squared. Lastly, don't forget to test edge cases. Try inputs like an empty array, weights that perfectly fit the elevator's capacity, or scenarios where all weights are identical. These tests will help ensure your solution is robust. This type of problem is closely related to several others that you might encounter on LeetCode. For instance, LeetCode 881, Votes to Save People, is a greedy problem where you pair people under a weight limit, which is conceptually similar. Another one is LeetCode 416, Partition equals subset sum, which deals with dividing weights into subsets with equal sums. LeetCode 322, Coin Change, is about minimizing resources under constraints, and LeetCode 1011, Capacity to Ship Packages Within D-Days, involves distributing weights efficiently using binary search. For alternative approaches, consider the two-pointers method. If you're allowed to reorder weights, sorting them first and then using two pointers to pair the lightest and heaviest weights is a great strategy. It's efficient with a time complexity of n-log-n, though the sorting step does add some overhead. Dynamic programming is another option, where you explore all subsets of weights that fit the capacity. While this guarantees correctness, it comes with higher space complexity and isn't ideal for very large inputs. Lastly, you might use binary search on the capacity if the problem involves minimizing it. This approach is efficient for large datasets, though it does require more complex implementation. Each of these methods has its trade-offs, so choose the one that best fits the problem's constraints and requirements. Great job! We've covered everything from the problem statement to the solution and key takeaways. Remember, practice makes perfect. Keep solving similar problems to strengthen your skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!